I think we're going to move on to our next talk, which is by Emily Riehl. So I'm just going to say a few words about Emily. She's an associate professor of mathematics at Johns Hopkins University, working on higher category theory, abstract homotopy theory, and homotopy type theory. She's published over 20 papers and written 2 books, Categorical Homotopy Theory and Category Theory in Context. She's been awarded an NSF grant and a career award to support her work, and has been recognized for excellence in teaching at both Johns Hopkins and at Harvard. A research monograph co-authored with Dominic Verity, which is on infinite dimensional category theory, is going to appear, I believe, next year. In addition to her research, Dr. Riehl is active in promoting access to the world of math. She's given interviews most recently for Quanta, Association for Women in Math, the radio program Science Friday, and the podcast My Favorite Theorem. She's given many talks, including at the Women in Topology workshop at MSRI and the Women in Math and Stats conference hosted by Gender Inclusivity in Mathematics at Harvard. She's also a co-founder of Spectra, the Association for LGBTQ Mathematicians. So I'm very happy to introduce Emily Riehl, who's going to talk for us on contractibility as uniqueness.
Great. Thanks so much, Anthony, and everyone who collaborated to put this together. It's a really wonderful event, and I'm sorry we're not in person, but we're making the most of it. So I haven't attempted to give a board talk over Zoom before, but I thought it'd be fun today. So I hope you'll bear with me, and feel free to shout if I write off screen. Right, so this talk is going to be about a way of redefining uniqueness to mean something a bit more expansive, or if you will, a bit queerer. It's a central idea to higher category theory, and so it's something that I find very appealing. And I'm going to introduce the idea starting an example, and then I'll end with something a little bit more concrete. So let's start by imagining your favorite topological space. Like this, and today the space will be called A. And part of the project of algebraic topology is to assign different algebraic structures to a topological space. So these all go by the name fundamental X. So one of these is called the fundamental group. So notation would be something like pi1 of A comma little x, where x is referring to some point in your space. And it's a group of paths, or I guess really I should say loops, x up to based homotopy. So a typical element of this group would be some path that starts and ends at x, but the path itself is not an element. It's really an equivalence path, equivalence class of paths like that, where the equivalence relation is something called homotopy. Okay, so there's an alternative. So there's something called the fundamental groupoid. So notation for this might be pi1 of x dropping, or sorry, my space is A. pi1 of A dropping the point x. And what this is it's the groupoid. Typical element is now a path. Again, sort of up to some sort of endpoint preserving homotopy. Say up to. Right, so the difference between the fundamental group and the fundamental groupoid is now, I can give myself a few more points in this space. A typical element of the fundamental groupoid is a path that might start and end at different points. But again, the path itself is not the element. There's an element is an equivalence class. So here I've drawn a path that's relatively similar to the first path. And the similarity is that I can fill in this space with a two-dimensional path. That's the meaning of homotopy. And the presence of that two-dimensional path tells us that the two paths I've drawn from Y to Z in yellow are the same. Okay, so then there's a final alternative. This is the fundamental infinity groupoid. The notation for this is pi infinity A. And the typical element of this is just a path. So we get to drop the equivalence classes at all. An element of this, again, is just, I'm going to give myself another point. Draw it in a different color just for kicks. So an element is really just the path itself and no longer any equivalence classes. So there's obviously some sort of trade-off happening here. The structure at the top, the group, is the most familiar, though its definition is in some sense the most complicated because you have to choose a base point, but the base point somehow doesn't matter, particularly if your space is path connected. The groupoid is a little bit less familiar, but it is something that is often taught in the first course on algebraic topology. It's an order of more complex than groups, but the benefit is now I get to just say paths between arbitrary points in the space as opposed to choosing some component for no real reason. But arguably the most natural structure, at least if you're trying to describe the algebra of paths in a space, is this infinity groupoid, because now we just have the points and we just have the paths, and we don't have any equivalence classes, we don't have any complexity there. The trade-off is that this thing is now some sort of infinity groupoid. So I have to explain a little bit about what kind of algebraic structure that is. This is something that's much less familiar. So let me try and introduce this fundamental infinity groupoid. So I'll tell you informally what it has. So an infinity groupoid is a name for an infinite dimensional kind of categorical structure, if that's an adjective that's familiar to you. So it has data in sort of all dimensions, and then it has a lot of composition going on. So I'll start with the data. So it has sort of points. Think of these as the kind of zero-dimensional objects. Then it has paths between these points. So these are sort of as kind of one-dimensional morphisms. We can think of as being some sort of objects. These are sort of one-dimensional morphisms, one-dimensional arrows, if you will. Actually, we got these arrows. It's a little friendlier word. Okay, then we have paths between paths, which are called homotopies. These play the role as the two-dimensional arrows. And then we have homotopies between homotopies. So we can do a path between a path between a path. Homotopies. These are the three-dimensional morphisms, but there's no reason to stop. So the infinity refers to the fact that this structure continues all the way up. So a path, let me explain a little bit about the dimensionality. You can think about the point as a map into the space from just the one point space. So that's a zero-dimensional object. The path you can think of as a map into the space from an interval, which is a one-dimensional object. These homotopies, like I've drawn in orange, you can think of as a map into the space from a square. So it's a interval cross an interval. So that's the square, and that's the 2 dimensions. These are maps from cubes into the space, or you can use different homeomorphic shapes if you prefer. So that's kind of the sense of the dimensionality. Okay, so this is the data of the infinity groupoid, but there's also additional structure, additional composition structure, which captures the idea that you can compose paths. So I want to say something about that. So maybe I'll phrase it as a question. How do we define the composite of so if you're familiar with this fundamental group, the more familiar structure, the group operation, the composition operation is composition of loops. So you do one loop, you do another loop. And similarly for the fundamental groupoid, so the question is, what do we do in this context, in this infinity groupoid context where we don't take homotopy classes? So part of the answer is, part of the answer is that we don't, or we don't uniquely. So we don't sort of define an operation. So unlike these other structures, we don't sort of define an algorithm for taking two paths and composing them, but we recognize when a composition is present. So I'm not going to draw everything on this picture anymore because it will get too crowded, but let me sort of illustrate down here. So if I have points, sort of X, Y, and Z, and I have some paths between them. So here's one specified path. Maybe I'll give it kind of a arrow-like letter, so F and G. So we recognize that a third path, so these things are all directed. The path F goes from X to Y, G from Y to Z. A third path, let me call it H, goes from X to Z. And whenever we have the data of a homotopy fills in the triangle here. And this really is data, so I should maybe give it a direction and I should give it a name. I'll do it in a different color and hope it's visible. So whenever we have the data of a homotopy, we recognize that H, this bottom path, is a composite of G with F, witnessed by the data of this homotopy alpha. So rather than have composition as an operation, we can sort of recognize a composite when we find it. So that's one new idea. And this propagates in all directions. So we need to also be able to all dimensions. We compose the homotopies between homotopies, but it's the same idea always. So, right. So again, rather than defining a composition operation, we sort of recognize in a setting like this that we can consider H as a composite, maybe not the composite, but a composite of G with F. So this leads to a natural question, which is how unique is this operation? So if composition is something that's being recognized, but not defined, how unique is it? So there are several answers to this question. I mean, one thing to say is that, so a partial answer is that it's unique enough for associativity. So unique enough for associativity. So any composition operation worth its salt needs to be associative. And let me illustrate the sense in which this composition operation, which isn't defined but witnessed by a path and homotopy, is associative. Okay, so I'm going to set this up by just drawing you another picture. So let's imagine points X, Y, Z, W. And if I'm interested in associativity of composition, I should start from 3 paths, maybe F, G, H. So this is a different H than the H here. Maybe I'll change my name, call that K. Okay, so to have a composite of F with G is to have a path K here together with a specified homotopy. Maybe I'll give it sort of more clearly a direction that inhabits this triangle. So this is some sort of 2-dimensional path. I realize the colors are a little light, but you can scribble on your own and imagine. So this is a 2-dimensional path connecting this sort of visible composite of F with G to K. Okay, so similarly, if I choose a composite of G and L, that amounts to choosing a path here, which I'm going to call L perhaps. And then I can choose a composite of Z and W. I realize now I didn't draw this picture quite in the way I intended it, so maybe I'm going to move that point down just a little bit. So to choose a composite here, I'm going to choose a third path. And so part of choosing a composite I didn't complete my drawing is I need to inhabit all of these with these homotopies. I wouldn't, the directions for the homotopies is something that you can pay attention to and think about carefully, but homotopies are like paths reversible. So if the directions are confusing me right now, pretend I drew it in a different way, because I might equally have drawn it in a different way. And if we look at this picture, it kind of looks like a flattened version of a tetrahedron. Maybe I'll draw that in white so that's perfectly clear. So here's my point, X, Z, W. So the paths, the 6 paths that I've drawn in orange form the boundary of a tetrahedron. I've drawn for you 3 homotopies. So this is a witness that K could be called the composite of G with F, that L could be called the composite of H with G, that M could be called the composite of L with F, or in other words, of H with G, parentheses, and then with F. And then if I choose a homotopy, or if I find lying around somewhere, a homotopy for the back triangle, the one between X and Z and W, that would then be a witness that the composite M here, which you might think of in quotes as being H composed G composed F, the data of the homotopy in the back triangle would witness that this can also be understood as H composed G composed F, because that back triangle is expressing the composite of this map H with this chosen composite of G with F. But really this is a 3-dimensional figure. I mean, a tetrahedron is a 3-dimensional figure, and the proper way to understand associativity in a higher categorical context is it involves not only the choice of the composite paths, And the homotopy is witnessing the binary composition operation, but also three-dimensional homotopy witnessing some sort of coherence between the choices made thus far. Now, I claimed that it is always possible that this operation is associative in this sense, and you can see that also from this picture. So I've drawn this sort of flat triangle thing, and now I want you to pretend that it's a tetrahedron. But an example of a tetrahedron is sort of a degenerate tetrahedron where it's really squashed flat. So I could compose up these homotopies alpha, beta, gamma. I mean, that just is a map from a triangle into the space, and here the sort of three-dimensional aspect is degenerate. And so that's sort of a proof that I can expand it into a tetrahedron. I can sort of expand it trivially into a flat tetrahedron. Okay, so that's, this is one part of the way of understanding, I mean, this is, the title was about uniqueness, so that this is going to be the central question. So one way of understanding the uniqueness of the composition operation in the fundamental groupoid is that it is unique enough for associativity, but there's something stronger that I can say. And the stronger statement of uniqueness is the following claim that then I'll prove. So the claim is that the space of composites of two paths, so this space of composites of two paths, again, these paths need to be composable, so connected end to end, is contractible. So to prove this, I need to define the space that I'm claiming is contractible, and then I'll show to you that it's contractible. So let's start by doing that. So remember, my ambient topological space is called A, and let me actually label some paths in A. So here's my path F. Here's another path, say G, landing in, I don't know, whatever point that is. So the claim is that the space of composites of F with G is contractible. That's what I'm about to prove. Okay, so the start of the proof should be giving a definition of that space. So how are we going to do it? So A is my ambient topological space. So remember the data of a composition, the way I said we recognize a composition, is I'm going to look at a map into A from this triangle shape. So you can imagine sort of the topological space that's a solid triangle. And if I map in to A, map continuously into A, then in so doing, I pick out points that are the images of the three vertices of the triangle. That's this W, Y, and V. And then I also pick out images of the three edges. Those are the three paths, the F and the G and the composite. And then the interior is giving us the homotopy that it witnesses the composition relation. So an arbitrary map from a triangle into A is a witness of some arbitrary composite between some arbitrary paths. But I want this to be the space of composite of two paths, F and G. So the way I'm going to do that is I'm going to restrict. So this is again a symbol for the topological space of continuous maps from the triangle into A. If I take this subshape of the triangle that looks like this horn, now I'm taking the image of just the boundary that's formed by the original two paths that I start with. And so I can pick out a point in this space, namely the point that's sort of F followed by G. So this again is the space of continuous maps that just trace out, that define the composable paths F and G. And if I take the fiber or the pullback, what this refers to is it's the subspace here comprised of continuous maps from this triangle into A that restrict to F and G along that one boundary. That's exactly the space that I'm trying to understand. So this is the space of compositions of F with G. A point in this space is a choice of composite paths together with the witness composite homotopy. Okay, so I claim that this is a contractible space. So let's try and understand this. So one way to say that a space is contractible, I mean, a meaning of contractible means that if I have any sphere of any dimension in here, Sn-1 is notation for the n-1 sphere, then that sphere can be extended to an n disk. That would be the sort of ball that sphere bounds. So if whenever I'm given a sphere in here, I can extend to a disk, then that would be a proof of contractibility. So what I'm trying to construct here is this continuous lift, this extension there. However, by the universal property of the pullback to construct this continuous lift, it suffices instead to construct this map in orange, and that's what I'll do for you. And how are we going to achieve this? Well, I can rearrange this commutative diagram. So along the top, I have a map from the n-1 sphere, Sn-1, into this function space. By adjunction, I can think of this as defining a map from Sn-1 cross this triangle into A. So this component here corresponds to a continuous map like this. But then along the bottom, I have a map from the n disk into A raised to the power of that wedge shape. So this defines a map from Dn cross that wedge shape into A. And because of the commutativity of this outer rectangle, these two maps that I've just defined are compatible on the common subspace, which is the n sphere across that wedge. Now, what am I trying to do in orange? I'm trying to extend this to a map from Dn cross that triangle. So I'm trying to construct a lift like this, but I can do this in complete generality, completely independently of what A is. We don't care at all what the homotopy type of A is or anything like that. And the reason is that this map emits a deformation contract. So if you sort of built this space for yourself, maybe in a case where n is 2, so we can visualize things a little bit better. It looks like a trough that like pigs would eat out of. So we've got, maybe I'll leave that as an exercise. And actually, sorry, n should be 1 for that to work out. It's like this, a trough that pigs would eat out of. But that's, whereas this is then the solid triangular prism. And this deformation contract idea means, again, I can sort of continuously, if I had, I don't know, I guess if you fill your trough with pig food and the pigs sort of eat it all down, you know, that's sort of the picture of the deformation retracted. That image is in anybody else's head and not just mine. Great, so this can be done in complete generality. And there's some sort of connection between this and this proof of associativity that I mentioned before, where we're trying to produce something 3-dimensional, but we do it by degenerating something 2-dimensional. That's related to the idea that we can use this deformation retract idea to prove uniqueness. Okay, so that was the example. And then in the last 5 minutes, I want to, I don't know, I want to say one other thing. So just the context, so let me connect this idea of contractibility back to uniqueness. So we were talking about something called an infinity groupoid, which is some sort of infinite dimensional analog of the perhaps a little bit more familiar notion of a groupoid. And one way to understand the difference between these two notions is here, so a groupoid is a structure that has composition, but composition is defined uniquely, sort of in the same sense as composition is defined for a group. If the oid is messing you up, whenever I say groupoid, just pretend I said group. So in a group, composition is a uniquely defined operation. So here we have uniqueness in the usual sense, so uniqueness as usual, where in this context, I have uniqueness sort of as contractibility. So in place of having a uniquely defined composition, I have this contractible space of composites. But there's an even tighter analogy between sort of the standard sense of uniqueness and the contractibility sense of uniqueness. And that's what I want to close by telling you about. So right, so let's just write down the sentence, sort of the logical sentence that says something or other exists uniquely. So, so I could say, so the sentence that says that A has a unique element. Or maybe I'll call it C, because this isn't the A from before. This is C has a unique element. So, so one way to say that is that it's a sentence that says there exists some X in C, so that for all Y in C, X is equal to Y. Okay, so that's sort of the logical sentence that expresses the idea that C has a unique element. So it can't be empty, so I need to have an element of C. But then if I had any other element of C, it's the same as the element that I picked already. Okay, but now let's imagine this statement sort of more constructively. So what I mean by constructively is let's not just think about the statement that C has a unique element, but let's think about how, let's distinguish between different proofs of that statement. Okay, so what I want you to imagine right now is when I write x equals y, I want you to imagine this is code somehow for the set of proofs that x is equal to y. And let's say we're just enumerating all the different proofs that you could have that x is equal to y. So then if I'm trying to prove contractibility, prove uniqueness, part of what I would have to do is for every y in C, specify a proof that x is equal to y. So I'm going to think of that now as taking the product over the elements of y and C of the proofs that x is equal to y. So the idea is, I mean, if you think about this product in sort of the category of sets, for each y and C, I'm going to choose a proof that x is equal to y. And this existential quantifier corresponds to taking a sum. So if I wanted to, the difference between this sort of logical sentence and this sort of more constructive sentence is here I'm imagining the set of all possible proofs of this fact. So how many different ways could I prove that C is a unique element? Well, I get to take the sum over all possible choices of element of C. I would get a different proof for a different base point or sort of center of contraction. And then I could, for every other element, I get to choose a proof that x is equal to y. So that's kind of these sort of superficially look the same. So if the sort of philosophy I'm after is a bit lost, then why don't we just go with that? Okay, but what's nice about the second formulation is it's code for an object in any locally Cartesian closed category. So and maybe I'll just say in a locally Cartesian closed category of spaces, this formula here, so this thing is code for a space. I'm going to call that space P of C. I mean, really, you would just call that space by this name, but I think that'll be a little more confusing. So I'm going to call it P of C. We can think of it as being some sort of predicate on C. So the C is because of that C there. Okay. The usual category of spaces is not locally Cartesian closed, but there are locally Cartesian closed categories of spaces. So maybe just grant me that. Okay, and let me try and explain how this works. So I'm going to build this space in sort of, how does this work? So in a locally Cartesian closed category, maybe this is the first thing to say. So in a locally Cartesian closed category, the symbols, there exists, and for all, or sigma and pi, refer to left and right adjoints to pull back, to left and right adjoints. If adjoint is unfamiliar, you can think of this as some sort of one-sided inverse operation, though it's not quite that, to pull back. Okay, so here's how we build this space. I'm gonna just describe this very informally. So first thing I need to build is the space of proofs that x is equal to y. And there's an analogy I want you to entertain. So I'm going to start by looking at the space of paths in C. So I is the standard interval. I can think of the space of paths in C. So I can evaluate at the endpoints, and that gives me then 2 points in C. And if I impose the requirement that those 2 points are the points x and y, and again take this fiber, what I have here is this is the subspace again of this, paths in C from x to y. So, and that's what I'm going to interpret this thing x equals y. I'm going to think of a point in this space, which is a path in C from x to y, as a proof somehow that x is equal to y. That's the intuition. Okay, and then I have a projection map here. So this is the projection onto the x coordinate, so the first projection, and then I have another projection over the single point space. So this is just sort of forget everything. And if I do this push forward operation of right adjoint to pull back, Then I'm going to get some space here. And then the left adjoint to pull back is just this. So this space here comes with a map down here. This left adjoint to pull back is just composition. So it composes that map with that map. And so the summary is that this space here that's produced by applying the right adjoint to pull back to this, or sorry, I guess it's related to this map, is producing this space P of C. Okay, so that's something that you need to go over a whole lot more slowly to actually understand it. But let me end by just describing what a point in this space is. So a point in the space C given by. So, and this is something you can read out of the universal property of this construction, which admittedly I've gone over rather quickly. So point of this is, so it's given by sort of a specified base point, this specified point, maybe I'll call it C and C. You can think of this as being the center of contraction. That's the choice of this X here. And then, so sort of for all, or I guess a continuous map. So the way this right adjoint to pull back is constructed is it's taking sections of some map. So it's going to be a continuous map from C into C to the I, so that when I sort of evaluate at the first endpoint, evaluate at 0, this thing here is going to be constant at the map C. So that sort of one endpoint is fixed C. But what is this? This component here is the data of a homotopy from the identity map at C, the space C, to the constant map at the point C. So in other words, the summary is that a point in the space is sort of a proof that C is contractible. That C is contractible. And that's actually the real idea of contractibility, is uniqueness. We started with the statement of uniqueness. We interpreted it in this locally Cartesian closed category of spaces. And we end up with the statement, not that C is unique, but that C is contractible. Okay, that's one of the starting points of this new area of homotopy type theory, but I think I'll stop there. So thanks very much.
Great, Emily. Thank you so much for a wonderful talk. And I think, June, we're going to unmute everybody so that they can clap.
Yeah, everyone's free to unmute and
Okay, Emily.